Okay. This is my favorite topic in the class. I think it's a really cool algorithm, and it's also going to be what you're going to be using for the class project in Easter. So I'm going to talk to you about stochastic dual dynamic programming, which is an extension of the nested decomposition algorithm that we saw last week. So I'm going to spend the next few minutes to review with you the nested decomposition algorithm, and so you can refresh it in your memories. And then I'm going to tell you what's wrong about it and why we need to move to something like SDDP. And I'm going to finish the class with an example. Now, I've promised you a convergence proof for nested decomposition, which we will do on Friday. So on Friday, Matthew will be absent, so I'm shooting for 2 hours of class. I hope I can have enough material for 2 hours of class, but it's going to at least be 1 hour, maybe 1.5, but hopefully 2. So on Friday, we'll also see the proof of convergence of the nested decomposition algorithm, which I've given you the recipe for how to do nested decomposition, but I never argued why it's the right way to do it. Okay, but if you can have a leap of faith for the next 2 days and believe that's the right way, then you'll also understand SDDP. Okay, so recalling what nested decomposition does. If you remember, our building block in nested decomposition was this problem that we call an NLDS. It's a linear program, and it looks at a specific time period and a specific scenario K. And what it contains is the immediate cost for that period and scenario, plus the cost to go, assuming that in the future we do things optimally. Now, this cost to go, like in the L-shaped algorithm, is a piecewise linear function of the x that we decide now for this scenario. And because it is a piecewise linear function, we can use these optimality cuts. Now, how we compute these vectors and matrices, we discussed it last time. I'm also going to show it in a couple of slides. But that's really the important thing to remember is that, again, like in the L-shaped algorithm, we're approximating everything with optimality cuts because everything is piecewise linear. We also have feasibility cuts in case from the previous time period we get an x that's making things infeasible for this time period. And we have the constraints that are associated with this time period, with this scenario. Okay, so we have these 3 sets of constraints here. So a reminder about the notation is the superscripts are time, indexing time. The subscripts are indexing scenario. So this script T indexes how many different scenarios we have at a different time stage. So again, if I can make a drawing here. In a tree like this, we would have, in time period 2, we would have scenario 1 and scenario 2. So superscript k to the 2 is this set of scenarios here. And, okay. Thank you. So the ancestor of, if I label this scenario 1, the notation used is that the ancestor of 1 in stage 2 is 1 of stage 1. Okay, so A of k for period t is the node that this node is coming from. And the x subscript ancestor superscript t minus 1 is the x that came to us from the ancestor of k in the previous time period. So it's a trial decision coming from the previous time period. Notation is clear. These are the dual multipliers that we use for computing the optimality and feasibility cuts. Okay, so how do we compute the cuts? Oh, before saying that, let's think first of all about how information is communicated among subproblems. So what we're doing is we're sending, when we solve an NLDS for a current time period and a current scenario, we can either send forward the resulting x. So we get a couple of things when we solve an NLDS. We get an x, and we get a bunch of dual multipliers. We can send the x that we get forward and move to the next time period. And the notation here is we send the xkt that we get from this problem, which is a decision variable for this problem, forward, and we move to time period t plus 1 and all the descendants of scenario k in period t plus 1. So, for example, if in this scenario tree here, the descendants of in period 3 of scenario 1 are 1 and 2. Okay. And so that's one thing we can do, and then we move forward. Or we could send multipliers back to the previous time period to build an optimality or feasibility cut for the previous time period. It's up to us how we move around in the tree, and that gives rise to different variants of the nested decomposition algorithm. For example, in the version I showed you last week, what we did is we scanned each time stage, and then when we hit the bottom, we went back. So first we started here, we got an x, we sent it to these two nodes, then we moved here. We solved this guy first, then this guy. We sent their x's here, 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 and here, and then we moved to the end of the tree. We got the multipliers, shipped them back to get cuts, shipped them back to get cuts. We solved this guy with the cuts now, shipped back the multipliers to get cuts for the first period. That was the protocol we used for nested decomposition last time, but you could walk around the tree in different ways. I think Matthew discussed this with you in the training section. Okay, any questions so far? Okay, moving on to refreshing your memory. This is an example, just what I talked about right now. So when we're designing the algorithm, when we're implementing it, we also have a data structure called direction, which indicates if we're moving forward or backward currently. So when we're starting from the root, we need to remember what time period we're at, what scenario we're at, what direction we're moving, and we get the output, x11, we ship it forward. So basically these slides are discussing what I just did on the board with my hand. So we go to the end, we get multipliers, ship them back for cuts. In period 2, we solve the problem, ship them back the multipliers for cuts in period 1. And these are the recipes for computing the cuts. This is the way to compute a feasibility cut. If you remember, I argued last time that the way simplex discovers if we're solving an LDS right now in period t scenario k, if it's infeasible for the x that we got from the previous time period, we're going to get a certificate of infeasibility, which is dual multipliers such that these constraints hold. Do you remember what the argument was for? Do you remember how we came to these relationships? How we arrived? Sorry? Come again? Exactly. So we were looking for dual multipliers which would be certificates of unboundedness of the dual, which would mean certificates of infeasibility of the primal. That was the idea. So we get these multipliers if the problem is infeasible in period t scenario k, and the recipe for building a feasibility cut for the current time period and scenario is by creating this matrix and this vector and sending them back to the ancestor. If you do that, you make sure that x never shows up again. And we'll see that in detail in the proof of convergence on Friday. But for what we care right now, we just get these pies and rows from the solver, we can use them to generate a cut. Okay, now if actually it turns out that all the descendants of a certain node are feasible, then we can just get their dual optimal multipliers, send them back to create an optimality cut for the previous time period. The way we do that is like so. So the matrix of coefficients of x is built in this way here. So we take the conditional probability of moving to this guy times the dual optimal multipliers of this guy times the T matrix of times the T matrix of this problem here, plus the conditional probability of moving to this node times the dual multipliers of this dual optimal multipliers of this node times the T matrix of this node, and that creates the T matrix of the previous time period, and that creates an optimality cut for the previous time period, and the same logic for the vector of the optimality cut. Now, here the difference with the L-shaped method is these elements here. So we need to be keeping a record of the dual multipliers of the cuts we already have. So over here, these we need to create optimality cuts, whereas in the two-stage L-shaped method we didn't use these, but in the multi-stage we need to store these and use them for new optimality cuts. Okay, so these are the recipes for executing the algorithm. So hopefully that kind of helps you remember what we've seen already. And now I'm going to tell you everything that's wrong about it and why we need to move to something more scalable. So let's consider the situation here. So we have capital H is the number of time periods. Typo, time periods, I'll fix that. And this is all, I should mention, this is based on chapter 10.4 of the book, but there's not as much information about SDDP in the book. Instead, the authors focus more on something they developed, which is called a bridged nested decomposition, which, since we're not going to implement it, I would say don't even bother with it too much. So as far as SDDP is concerned, you can read the stuff in chapter 10.4 that's about it, but then you will probably need to use the code that I will give you in these slides, as well as Mario Pereira's paper, which I'll upload as a source for better understanding it. Okay, so a bunch of the stuff you'll see in the next couple of slides are not in the book. Okay, so we have, but the notation that I'm using is from the book. So we have capital H time periods, and M superscript T denotes how many nodes we have in each time period. So in this case, we have one node for time period 1, so M superscript 1 is 1. We have 2 nodes for period 2, so M superscript 2 is 2. M superscript 3 is 4. Now, the question for you is, where did I get, okay, sorry, I will exit the handout version so that I can torture you with questions. So I'll need to compile that first. Then again, you can show up with the printed handout slides and answer the questions anyways, but okay. Right, so the question that I have for you is, when we do the forward pass how many LPs do we solve? For this tree here in particular, can you count them? 11? 11 or 7? It's, the way I've drawn it is maybe a bit confusing. The way you can also think of that drawing there is like this. It's just that the 4 guys here, for the descendants of 2 are identical to the descendants of 1. But this is really what the tree looks like. So the answer would be 11, yeah. 1 plus 2 plus 4 plus 4. Okay. Backward pass. Nope. Because the forward, I want to say 2. Because in the backward pass, we don't solve the root. There's nothing to send back. We're counting the root as part of the forward pass. Details, but just proper counting. So that's where these formulas here come from. So I'm summing from 2 to h minus 1 for the backward pass. So here you can see how this becomes pretty nasty if the tree becomes rich. So if I have, basically you get an exponential number of linear programs that you need to solve as you're looking further and further down in time, right? If every one of these nodes then has 4 children, this thing will explode. If you do this forward-backward pass in a blind way without being a bit smart about taking advantage of some information, this becomes non-scalable. So you would ask, why did we even bother learning about it then? And that's basically, it's really helpful to have Matthew look at the slides before I show them to you, because then he can preempt these questions, and I don't like, it's better motivated that way. So why did we even bother learning about it is that in extended form, if you had tried to, so let's suppose we have 20 time periods here, and the scenario tree is enormous. With extended form, which means writing it out as a single linear program, you would not have even been able to load it in memory. Here, at least you can load it in memory, but it's, practically speaking, is never going to converge. It's just going to go on forever. So there is some steps forward, but the more important thing is that, so it's not the same thing as extended form, it's a different approach to the problem, but the more important thing is that it creates foundations for heuristic algorithms like SDDP that we will see today. So nested decomposition is, I think of it as kind of like a building block to understand other algorithms rather than an algorithm that you want to actually be using. Okay, so now I'm going to use 2 words here, enumeration and simulation. So what kills nested decomposition is the fact that when we're doing a forward pass, we're doing enumeration of all the possible scenarios. And a different approach to solving the problem would be to simulate scenarios. So what would be an enumeration of the nodes here? If this guy is 1, this guy is 1 and 2, and this guy is 1, 2, 3, and 4, enumeration is counting all the possible ways you can start from time 1 and end at time 3. So how many elements would an enumeration of all the scenarios have here? We kind of answered that before. No, sorry, we didn't answer that before. 8. 4 plus 4, 8, right. So there's 8 ways to arrive to the end of time. If I'm looking further and further down for more and more time periods, this becomes the set of possible ways to reach the end of the tree grows exponentially with the number of time periods. So an enumeration is not scalable as you look at more and more time periods. Instead, what we can do is simulate a bunch of scenarios, and there we control how many scenarios we simulate, so we restore something that's scalable. So for example, in our tree here, like Leopold said, we get 8 possible enumerations of starting from the beginning of time. I haven't included here this node just to make the notation concise, but there's 8 different ways you can start from period 1 and go to the end of time. Whereas, for example, if I did a simulation and I imposed in my code that I will only look at three samples, I don't know which ones. I'm going to generate them randomly, but I can control how many I generate. We could get, for example, these 3 samples here. So we might throw the dice, get for time period 2 this outcome 1, and then throw the dice given this outcome for the last time period and get node 3. Then another simulation could produce 2, 1, and another simulation could produce 1, 4. Okay, so the idea with SDDP will be to, instead of going through all the possible combinations of things that could happen until the end of time, let's code some dice and put them in our code and just randomly simulate walks down this tree. Okay, that's the idea. And you'll see it in the example how it works specifically. Now, that helps us. It helps us because now we don't have to solve an exponential number of linear programs. If we generate capital K samples, how many LPs would we need to solve for forward pass? K times the depth. Exactly. K times H. So the question now is, does this help us in any way in solving the problem? But clearly, by simulating instead of enumerating, we get something that grows linearly with the horizon. So that's the benefit. So that makes our life easier for the forward pass. Now, the problem is that as opposed to the nested decomposition algorithm, where we have a guarantee of finite convergence, even if it takes forever, we have an algorithm that is guaranteed to go to optimality. When we're simulating, we're going to get samples of costs, and we're going to get a termination criterion which will be probabilistic, and I'll explain exactly what that means, both rigorously as well as in the example. But we are now entering a zone of simulation, so termination criteria now become fuzzy, somewhat fuzzy. Okay, that's the thing to remember for the moment. Now, as far as the backward pass is concerned, we're going to do a really cool trick that Mario Pereira came up with, and well, I talked with them yesterday, and they told me that they can handle problems even without this trick, but it's one of the things that makes the algorithm extremely powerful. So if you want to make this assumption, the algorithm becomes super fast. The trick that we're going to do, it requires, it's an assumption we need to make, is the assumption of serial independence. And once we make this assumption, we can accelerate the backward pass. What does serial independence mean? It means the following. The transition probability into any of the nodes of period t is the same wherever you are in period t minus 1. So the transition probability from this node to this node is equal to the transition probability from this node to this node. The same for this guy. transition probability here is equal to the transition probability here, which is basically all I'm saying is that the distribution of these outcomes is independent of the path. That's all I'm saying. And you can think of processes that violate this assumption. For example, another regressive model. If you remember, we saw another regressive model of uncertainty back in lecture 5 or 6. There we had random demand in period t, which was equal to random demand in period t minus 1 plus some noise. So basically, when you're looking at the beginning of time, for example, you have a certain level of demand in time period 1. You start from a certain level of demand. Then you can approximate the demand in the next time period with a bell distribution. So you have an unlikely outcome here, an unlikely outcome here, a more likely outcome here, a more likely outcome here. Because the demand you get in this time period is this demand plus Gaussian noise. And then when you're looking in the future, if you have a range of possible demand outcomes, it depends, the likelihood of landing in any one of these depends on where you start here. So if you start from this node, the PDF of landing in these nodes looks like this. So it's more likely that you land, for example, in this level of high demand over here. But if you start from a very low demand, it's more likely that you land in this node over here. You see what I'm saying? The distribution of demand in period 3 really depends on where you are in period 2. Whereas serial independence says, no, the distribution of the random variable in period 3 doesn't depend on anything else. It's fixed. Okay, so that's serial independence. I also have some examples to play with so we can get a feeling for it. So if this is our tree, the question is, and the notation here is the numbers on the lines are transition probabilities, and the numbers in the circles are values of the random variable for that node. So question to you, is this tree serially independent? The reason being?
If you are 1, you cannot derive from 2.
Right. So, right. So the future looks different because of the values of the future, not the transition probabilities, but the values. Another thing to check when you're given a scenario tree is if it corresponds to the probability distribution. So you want to make sure that the sums of these things always sum up to 1. Okay, how about here? I think you get the idea, but let's look at 2 more examples. So how about here? Again, the reason, because the future from 2 looks different from 1, okay, so you get it. So here, note I've changed the numbers. Serially independent or not? Yeah. It is. Doesn't matter that I've changed the numbers here because there's only one node from the path. But the important thing is when you're sitting at 1 or 2, the future looks the same, regardless. That's now very important for the following reason. Intuitively, the v of vt plus 1 of xt, do you remember what this represents intuitively? I know you haven't done dynamic programming, but I've mentioned this a couple of times. So when we're solving an NLDS and we're doing minimize C xkt plus theta, the theta is approximating the value function. The value function is the best it's the best possible cost you can get if you do things optimally from time period t until the end of time, given that you're at this specific node of the scenario tree right now. So if the future looks the same from either of these two nodes, the value function is also the same. So that means we can share optimality cuts among different nodes. If we did not have serial independence, the future would look different depending on where you were in each of these time periods. So the value functions would be different in each of these nodes. So you would need different cuts for different nodes. Okay, but if the future looks identical, then the expected cost to go is the same, no matter which node you are in here. So whenever you get an optimality cut for this node, you can also send it to all other nodes in the same time stage. Okay, again, intuitively the reason being that the future looks identical no matter where we are sitting in the current time period. So, this is starting to look promising now, because I've told you a way we can avoid enumerating just by simulating. So that gave us k times h linear programs in the forward pass. And now I'm going to propose that in the backward pass, we just solve, well, actually, let's see this in the drawing. So at the forward pass, we solve, at each forward pass, at a single forward pass, we solve capital H problems. So then if I do k Monte Carlo simulations of what could happen, I solve k times h linear programs. And I store the x's for each Monte Carlo simulation. Okay? And then, after I'm done doing these scannings, they're all forward scannings, I haven't done anything backward yet. Then I solve starting from the bottom of the tree, I solve all the LPs for each of the x's that I got from the Monte Carlo simulation. The idea of the algorithm will be the following. When I'm doing k Monte Carlo simulations, I'm going to store for each of these the x, the resulting x vector, from period 1 until the end of time. And these will serve as trial decisions for generating optimality cuts. Okay. So remember, every time we're doing an optimality cut, we're simulating a v of x, so we need a trial x to create a cut around. So this forward pass serves as, in order to generate capital K trial x's. Okay, we generate these with the forward pass, then we do the scanning of the tree backwards. So what we do is we solve all of the nodes in the end of time, but the trick is we pass the resulting cuts to both of the nodes. Why? Because the value function is the same for both of these nodes. The future looks the same, sitting from both of these nodes. That's what I'm saying here, okay? So, what the slide is saying then is that for a given trial x, so I should have, the notation here should have been x from t equals 1 to capital H. For a given x, starting from the beginning of time to the end of time, we solve these many LPs, but then we have capital K of these sequences, so we solve this many LPs k times. And that's the amount of computation required for a backward pass. I know this is a lot to take in half an hour, but we'll see an example and a bit of code, so hopefully that'll be clear. So, in case you've understood this, how many LPs do we need to solve for a single backward pass here? Remember, for a single backward pass, we just scan the whole tree to send cuts back. We don't need to solve the time period 1 because there's nothing to send back. So how many LPs do you think we solve for a single backward pass? 6 it is. And how many cuts do we generate? It's one of the 3. Which one? Who goes with 2? 3. So there's 2 for time period 2, 1 for time period 1. Okay. So now, if we had 10, 3. It is 3.
Yes.
Oh, okay. 1 here. So, well, 1 here. The same one here. It's the same one, but if you hadn't done serial independence assumption, you would count it as 2. So then also 1 over here. So it's 3.
And the one?
Here we don't have automatic cuts. Okay. Because at the end of time, there's no future. There's no.
So with serial independence, it's
En effet, oui. But if you looked at this in the code, it's really just 2. That's correct. But if you thought of this in terms of nested decomposition, it would count as 3. Okay, but really it's just 2. But to think of SDDP, I recommend to you to think in terms of a scenario tree like this, and although in the code you will not have separate code for, no, in fact, I take that back. Sorry, it is in the code, it's also in fact 3. Because we have, in our code, we have a different, we're storing this problem as a different problem from this one. But the cuts that we pass are the same. So even in the code, it's actually 3. Is that clear what I said? We have a different storage for each of these NLDS. So whenever we get a single cut from here, we send it to the storage of this problem as well as this problem. So it's 3. It's 3. Sorry for that.
But then it's the other section, right?
No, because the uncertainty is different for each of these NLDSs. The H, the H vector, yeah. That's really what makes these 2 nodes different. It's the H vector. So they are different problems, but with the same cuts. Okay. I was about to draw something, but we got it. Okay, so that's the idea. Now, okay. Matthew raised this up last year, and then he raised it up again when he went through the slides with me on Monday, and then I emailed the Brazilians and asked for clarifications. So the truth is that you don't need serial independence to make SDDP work. It's just that it makes your life much easier. The idea I'm going to show you, yeah. For this here, there are no optimality cuts. There could be feasibility cut. Not feasibility cuts either. Okay, let's take these things one at a time. Do you understand why there are no optimality cuts? The idea is that each NLDS, think of it as an LP that describes cost you pay right now plus future cost. The future cost in its full functional form is a value function, but we don't know a value function, so we're approximating it. So we're using a theta. But when you're in the last time period of your problem, there is no future cost. So you remove the theta from the problem. Or with the code, you fix it to 0. Okay, that's why we don't have a value function or optimality cuts. Now, why don't we have feasibility cuts? We're not sending an X to anybody in the future. So there is no multiplier sent back to us from a future problem that creates a feasibility cut for this time period. If you remember the expressions in nested decomposition, for NLDS of time period T, scenario K, a feasibility cut looks like this. And the way we created this matrix and this vector is... We do send back. We can send back multipliers to create a feasibility cut for H, capital H minus 1. But for capital H, no matter what we do, we're not afraid of it. Is that better? Okay. So, like I was saying earlier, you can apply the same algorithm that I'm going to show to you, even without an assumption of serial independence. But it's just going to require more memory and more approximations. So if we did not have serial independence, in this problem here, we would be trying to approximate 2 value functions, not 1. Which means, in general, we would need more cuts for the algorithm to converge. Also, we would, well, actually the storage, that's a mistake I'm making in the slide. The storage is the same. It doesn't change because we have storage for both of these problems, even if the cuts are the same. So the memory is the same, even without serial independence. But what changes is you need more optimality cuts without serial independence. So I'll correct the slide and remove this. Okay. Now, I wonder if this is a good time to take a break. Well, I think we have until 11:15. I think we have 12. I think we have time to also see the algorithm. Okay, so this is what the algorithm will look like. I want to create. I'm going to start with a forward pass. When I'm at time period 1, I just want to create a seed for k streams. So what I'm going to do is I'm going to solve NLDS1 and store the resulting x repeatedly for capital K times, where capital K is the number of my samples. So basically, all the samples start from the same trial x. And the reason, again, remember, the reason we're doing a forward pass is to generate trial x's, capital K time series of x. So we solve the time period 1, scenario 1, and then we start marching forward in time. So we're looping first over time periods, then over scenarios, which means we are looping yeah, I was afraid of that. So we solve this guy, we store the x k times, 1, 2. It's the same vector, but we're going to store it k times anyways. Now we're going to move here, and we're going to scan these 2 guys, generate a bunch of x's, but I'm going to solve this problem capital K times. So the first time I'm going to solve it with input from here. The second time I'm going to solve it with input from here, and so on. The resulting x that I get from solving it with this input, I'm gonna create another data structure. So I'm gonna store here another capital K x's. Maybe instead of drawing it, it's easier to actually look at the slides. So I'm looping first over time periods, then over samples. Sorry, mistake. I'm not gonna scan these guys. I'm gonna sample this randomly. Sorry, that was a mistake. So the first sample I might get might be node 2. I'm gonna solve this NLDS with input from the first x and get a new x here. So I'm gonna store that as my first x for time period 2. Then I'm gonna roll the dice again. Maybe I get node 1. This second time I'm gonna solve it with input the second x. And I'm gonna store that over here. Then I roll the dice again. Maybe I get node 1 again. I'm gonna solve it with input from the third x from the previous time period. Store the result over here. So if you see what I'm doing, I'm rolling the dice, picking one of these guys at random, and solving it for the corresponding trial ancestor, basically. Okay, that's the idea. So what I get at this period is also capital K x's. I march forward, I do the same. I roll the dice, land in one of these nodes randomly. Should be like this. And repeat this process. So what I get in the end is capital K time series of trial x's. Okay? So that's what I'm describing in the code here. Loop over time, loop over samples, pick an age randomly. So the only source of uncertainty in these problems is the age. Solve the resulting NLDS of time period t corresponding to sample I. And because I'm corresponding to sample I, I'm using xi from the previous time period. Okay? And what I'm going to do is solve this as the next outcome for this sample I. Okay, but graphically, it's kind of what I did on the board with my hand waving. That's the forward pass. So that gives us, again, here we're going to get, in this last period, a bunch of x's, k of them. So that gives us one sequence of x's, two second sequence of x's, and so on. So it's going to give a capital K sequence of x's. And what we're going to do in the backward pass is loop over time periods, loop over scenarios, and basically generate the optimality cuts. So what I'm going to do is I'm going to loop over all of the scenarios of the last time period, but solve them for the xi of the previous time period for all possible I. So that's going to give me k optimality cuts that I compute like this. So again, here I'm looping over all the possible scenarios of that time period, and I'm solving the NLDS that corresponds to that k with this trial decision. And I'm going to solve this for all possible trial decisions. I'm going to generate all the possible optimality cuts. Okay, just remember that in the backward pass, we're generating tons of cuts for the previous time periods. So basically, every time we complete a forward pass and then a backward pass, and we do the new forward pass, we have a much more detailed representation of each of the value functions. That's important to remember. Okay, now, here's where the side effects of doing a simulation come in. So, what we get from a simulation, so let's think about when we would terminate this whole process. Can you think of a lower bound for this problem? From this algorithm. So I told you what we did. We go forward capital K times, and then we do capital K backward passes, which are generating a bunch of cuts that get sent back. How would you get a lower bound? Do you remember how you got a lower bound in an LDS? Come again? Of which problem? The root. Right. So we saw the objective function value of the root. In that respect, nothing has changed compared to nested decomposition. So again, we're going to use when we're doing a forward pass, we're going to use the optimal value of the root as a lower bound. And that is a real lower bound. There's no approximation involved there. The thing is that with this process, we're not guaranteed convergence in finite number of times as we were in nested decomposition. And either way, we don't want to wait for that long anyways. Now, intuitively, what helps you understand SDDP is the fact that every time we're doing a forward pass and then a backward pass, we get value functions here that are becoming richer and richer. So maybe in the first forward pass, and then once we complete the backward pass, we get a bunch of optimality cuts like this. Then the next time we move forward and then backward, we get richer and more richer description of the value functions. But the thing is, we don't want to wait until the W equals the theta, because that's going to take forever. So the termination criterion is the following. So as we're doing forward passes, we get the x's, sequences of x's, capital K sequences of x's. We can compute a cost associated with each of these sequences. Okay. All we need to do is multiply the C vector for that time period times the x for that time period. This x that I get as I'm moving forward, in fact, the sequence of x's, is a feasible solution for the problem. So a good way to create an estimate of the average cost, well, maybe for me the easiest way to think about this is the following. Suppose I terminated SDDP after doing 5 forward-backward passes, okay? I would have a bunch of optimality cuts here. Now, these optimality cuts, basically, they give me an oracle, a way to create x's. So if someone walked up to me and told me, did you solve this problem? I would tell him, actually, no, but what I have for you is a bunch of optimality cuts and a bunch of NLDS's. So instead of telling you an x for each scenario in each time period, I can give you all these linear programs, and every time you want to decide what to do, you can solve an NLDS for that time period, and that will give you an x. It's something to do. It's not maybe the optimal thing to do, but it's a way to generate a decision for each time period, for each scenario. And so, obviously, if I spend a lot of time doing 100,000 of these forward-backward passes, the value function approximations are going to be much, much more accurate. So my answer to this guy who walks up to me is going to be much, much better. I'm going to give him an LDS that's much, much more detailed and complete. But in any case, if I prematurely stop the SDDP algorithm, I will have a bunch of cuts that I can hand back to this guy, And that way, he can generate sequences of x's depending on where he is in the scenario tree. This policy that results from applying this oracle will give me an upper bound estimate. So basically, if I compute the cost of using this oracle, I can do that capital K times. I'm going to get capital K different costs, zk. Each one of them is computed as the cost for that time period times the x we get for that time period. And we get an estimate of this average cost by just taking the sample mean. So here's a question for you. Suppose I interrupted SDDP. I handed back each of the NLDSs, and then I did 2 forward passes using these NLDSs. Would the costs, would the different costs be? These costs are going to obey some distribution, right? Now think of these costs as random variables. Are they going to depend on each other? Don't you think so?
Yes.
How come you think they would depend on each other?
Because we generate capital K difference.
So you're saying we're generating capital K
Different fire.
Mm-hmm.
So I think it will be
Let me ask a different question. Suppose that I tell you, you are a trader, I give you €100 to play tomorrow in the stock market. And I tell you, bet on this stock in the morning, and just buy it in the morning, sell it back in the evening, and walk up to me with the cash. Now, how much cash I'm going to give back to you is a random variable, which depends on the trajectory of the stock. But assuming that from day to day this stock does the same trajectory, is the amount of cash I'm going to pay back to you dependent on what I paid back to you yesterday? That's the way to think of SDDP. What I described to you, buy the stock in the morning, sell it in the evening, is a policy. The same way, if I interrupt SDDP prematurely, what I get is a policy, a way to generate excess. So depending on when we're simulating forward, depending on the specific sample, with this policy that you follow, you're going to get a certain cost. Then if you get a different sample, you're going to get a different cost. But these two costs, if you're simulating these outcomes independently, these two costs are also going to be different. I don't know if that's at all clear. Again, intuitively, the way to think about it is that when I prematurely terminate SDDP, this is a machine that gives me a policy, basically, a way to do things for each time period, for each scenario. So maybe the example wasn't extremely helpful, and it's probably easier if you see a specific case, but these ZKs will basically be independent of each other. And when I'm drawing independent samples of something, and then I'm taking their sample mean, what do we know from the central limit theorem? If you recall. Right. Okay, and the standard deviation is estimated by this formula here, and the mean of the bell curve is estimated by this formula here. So Mario's idea was that when is a good time to terminate SDDP? Well, that depends. I mean, when I'm doing a forward pass, I get k independent samples of cost. So let's look at the bell curve. Let's think of the bell curve, how it would look like. So basically, the termination criterion is this. I know the lower bound from solving from the objective function value of the root node. And then, every time I do a forward pass, I can estimate a bar z. Now, this bar z will have a Gaussian distribution. So, if my lower bound lands close to this estimated upper bound, that's a good time to stop. The intuition is the following. The first time I do a forward pass with SDDP, I'm going to have no value function approximation. So at every time period, I will be doing the most greedy thing possible, solving only for that cost. That's going to be it's a way to do things. It's going to be a really crappy policy. So its average cost will be very high. So basically, this bar z will be all the way up there. The z lower bar will be all the way down. And this termination criterion will not be satisfied. But as you generate more and more optimality cuts, you're getting better and better approximations of the future cost impact. So your policy is going to be better and better. So this bar z is going to be going down and down and down until at some point it comes close enough to the lower bound, and then you stop. That's the idea. Again, we'll see the examples, so all of this is going to become much clearer, and perhaps this last bit of information, I'm going to save it for after we solve the example. So the last thing I want to tell you before we take the break is just a quick overview of the SDDP algorithm. We initialize our upper bound is infinite. We start with a forward pass. We store the lower bound, which is the objective function value of NLDS11. If it's in this interval, we stop. It can't be first time around. If it's not in this interval, we go to the backward pass. Then we do the backward pass. After we're done with the backward pass, we return to the forward pass. We check, now after we've generated a bunch of cuts and we have a new estimate of the upper bound, we check our termination criterion again. If it's not satisfied, we do a forward, backward pass and so on. So this is the algorithm, and I'm going to cover an example we've seen already with nested decomposition. Hopefully after you see it, things will become more intuitive. Alrighty, so let's see an example. This is the air conditioning example that we've seen before. I'm going to give you a quick reminder. We're producing air conditioners for 3 months, so it's a 3-stage problem. Right, so the maximum production we can have is 200 units per month, and we can produce overtime, but it costs 3 times as much. So the normal price of producing is $100 per unit, but if we want to use overtime, we pay $300 per unit. And we have, forgot to write this in scenario 3, equally likely low or high demand, 1 or 3 in time period 2, well, 100 or 300, and then equally likely low or high demand in the last time period. So these are. So here we do have serial independence, right? You see it. The future standing from here to here looks identical. It's 1 or 3. Demand is 100 or 300, and both are equally likely. So we can share cuts. We can also store demand, and that's half as expensive as producing it. It costs $50 per unit, and all demand needs to be met. We've seen this example before when we did nested decomposition. So the notation that we're going to use is X for regular production, Y for storage, and W for overtime, and D is the demand level. Okay, so here I'm just describing what you already see over there. So 2 nodes effectively in each time stage, equally likely probabilities, and demand is 1 or 3. If you write the problem in extended form, it looks like this. And what I've done for you in the tree here is I've drawn the optimal solutions for you. So suppose you had a way to get. So suppose you had solved the extended form problem. What would the distribution of your costs look like? If you play this every 3 months, the same thing happened over and over, and you always behaved optimally, what would the distribution of your costs look like?
Maybe just 4 activities.
4 bars.
Just 4 bars.
Let's see the scenario of low demand, for example. What would be the cost?
What the first one?
Yeah.
Right. 0.
We produce 200. We pay the regular price of 100 per unit, and we store 100, and that costs 50 per unit. So here, well, let's like normalize everything. So we pay a cost of 2 for production and 0.5 for storage. Then when we arrive here, we observe the low demand. We pay 1 for production, but we also carry 1 over in storage in case we get a high demand over here. So we pay 1.5. So the total cost is 2.5 plus 1.5 is 4. Again, if the demand we get is low-high, you go again through the calculation, so it's 2.5 plus 1.5 plus 2. So that would be 6. If we get high demand, low demand, then we pay 2.5 plus 2, that's 4.5, plus 1, that's 5.5. And if we get high demand, it's 2.5 plus 2, 4.5, plus to 6.5 plus 1 emergency, which costs 3, that goes to 9.5. So our histogram would have a weight of 25% at each of these values. This must be wrong. 2.5, 1.5, 4. No. Okay. Might have error. Yeah. Anyway, we'll see. So this is the, assuming you know what to do, you've been able to solve this problem, and this is the distribution of your cost. Now back to Tom's, the discussion I had with Thomas earlier. If you let this 3-month thing happen over and over, what happens in one sample as a cost is independent of what you would observe in another sample. Okay, this is your optimal policy. This is how you react to uncertainty. Each sample of uncertainty is independent from each other sample of uncertainty. So the cost you incur at each sample is independent of the cost you incur at each other sample. Okay, so if you had let SDDP run up and down this tree forever and generate all the possible optimality cuts that you could generate, it would eventually give you the same behavior. Why? Because it would approximate all the value functions exactly, and you would always get the optimal x every time you're sitting at a certain node. So if but the thing is that you might interrupt SDDP prematurely and get suboptimal approximations of the value functions, and therefore suboptimal reactions to uncertainty. But the key thing to observe is that if you interrupt it prematurely and then repeat this episode over and over, the independence conclusion holds even if you're acting suboptimally. If once you have a policy, a way of reacting to uncertainty, and uncertain outcomes realize, and you react according to your policy, your costs, given this policy you're applying, are independent from realization to realization, whether this policy is optimal or not. It's the way you react to the world. The world sends you outcomes in independent ways, so the costs you incur are independent of each other. You can do it in a good way, in which case your average cost is lower, or in a bad way, in which case your average cost is higher. So in the code that I will give you, and you can use it for your project or not, it's up to you. You might want to code this from scratch to understand it better, but you might also want to see how it behaves on this model. Also, the other problem of using the code I'm going to give you is it's generic. So for a specific application, there may be more efficient ways to implement it. In any case, these are the last 6 lines of the code. Well, this is one of the first lines of the code, and these are the last 5 lines. So I'm defining a param called cost record, and it's indexed over Monte Carlo samples and iterations. So what I'm doing is after I'm done with everything, forward passes, backward passes, I store in this data structure for Monte Carlo sample M and iteration. By iteration I mean, is it the first time I'm doing the forward backward pass? Is it the second time? That's what I mean by iteration. Okay. The forward backward pass might have 100,000 different Monte Carlo samples, but the I index is counting whether it's the first time I'm doing this, or the second time, or third time, and so on. So this data structure holds the cost of my policy. It might be a suboptimal policy, but that's what it stores. So this X trial record is indexed over decisions, time periods, Monte Carlo sample, and the number of iteration. So it just basically remembers what you did for that Monte Carlo sample, for that iteration, and it stores the cost. And then I'm taking the Oh, yeah, then I'm looking at the last iteration. That's the last iteration is basically the one where I'm done approximating value functions, and that's the point where I stop the algorithm with as good an approximation of the value function as I could, given the time I wanted to spend. So it's the best possible performance I can get. So in cost samples, I'm storing the best possible performance I can get, basically, for each Monte Carlo sample. Okay. Why? Because it's the last iteration. And then I'm averaging that, and this will have a Gaussian distribution. Okay. If I did this repeatedly, ran this code repeatedly, and looked at this cost average, this thing would have a Gaussian distribution, and I'm calculating its standard deviation. Now, let's think a bit what we can expect from this algorithm as an algorithm. So, like I said, this cost record structure is storing Monte Carlo sample and iteration. So its rows are the Monte Carlo samples, iterations are the columns. What is the distribution of each column? Is it Gaussian? If I had if I had all the optimality cuts that describe fully the value function, what would the distribution look like? Exactly. It would be 4 bars like this. Great. How does row K column I compare to row K plus A column I? They're independent samples. Okay. Which column is more likely to have a lower average? So I take the average of the first column, the second, until I'm going to show you results for 5. So which is likely to have the lowest average? Left. So you got it. Come again?
Why is that?
Because at each iteration, after I'm done with the iteration, I get a more detailed description of the value function, so I'm more likely to make good decisions that thing. And the data that has a Gaussian distribution is if I look at the average here, then throw everything away, rerun the algorithm. And again, look at the average here, throw everything away, rerun the algorithm. Look at the average here. This is the data structure that will have a Gaussian distribution. Okay, now for the example I'm going to show you, I ran the, so this one is for 5 iterations, 5 times backward forward, with 100 Monte Carlo samples in each iteration. And this is the distribution I get at the last column. So 4, 5, 5.5, I was afraid. Okay, I probably screwed this up in Excel, so these bars need to move to 5.5 and 6. Sorry. And if I had 100,000 iterations instead of 100, these bars would be more or less at the same level. Okay. And this is not. So I'm pointing out this is not a Gaussian distribution. Here, the central limit theorem doesn't apply to this data, right? It has nothing. The central limit theorem has nothing to do with this data. And here's what the SDDP algorithm looks like. So what you're seeing here is a plot of the what I'm doing is taking the moving average of each of the columns. Okay, so I'm taking the moving average of this and plotting it with respect to the rows. Okay, so you expect this moving average to converge to average cost, basically. And that's what you're seeing here. There's a couple of things to note from this plot. So, first of all, the moving average has a lot of noise in the beginning. Now, what is striking about the graph? So basically, here you see how the algorithm learns, right? In iteration 1 and 2, it's behaving, in iteration 1, it's just really bad. It's crappy because it's only looking at current period cost, ignoring value functions. So it's just doing the optimal given the cost in that period. But that's creating problems further down the line. So the average cost is high. Same for iteration 2. It hasn't learned the value functions yet. But in iteration, in the remaining iterations, it discovers the value functions. And in fact, this is the optimal cost. So this is really close to the lower bound, basically, what you're seeing here. This is a small problem, so it converges, but in a bigger problem, it's harder. Okay, so the things to note, the standard deviation. So we store that in cost SDDP. Monte Carlo count 100 samples, 5. Okay, let's think a bit about these, like implementing this. What are the trade-offs here? So, what's the good thing about it? Increasing this iter count, setting it higher in your code. Yeah. Yeah, you get more learning. So you're expected when you interrupt to have a better policy than if you had run fewer iterations. But the price you pay is the extra computation of the forward backward passes. How about here? What's the trade-off of increasing or decreasing Monte Carlo count? Why? I mean, why not have Monte Carlo count equal to 1? Something very small. Of what specifically? Not the optimal cost of the problem is right. So it's the upper bound estimate. Basically, you want to get a lower variance of the upper bound estimate. Okay. Again, the trade-off is if you increase this, then you spend more time at each iteration. Okay. And then I had this formula which I produced. Okay, so here's a question for you. And let's try and derive this formula on our own. Suppose I wanted to get a 1% optimality gap in my problem with a 96% confidence. So how many Monte Carlo iterations would we want to run? So again, the statement I'm making is I want to decide how many Monte Carlo iterations to set. And I want to make sure that 96 times out of 100, if I interrupt my algorithm using the termination criterion I showed you earlier, then is that what I want to say? Right. What I want to say is that, yeah, 96. Sorry. think what I want to say is that one percent optimizing, yeah. I think what I want to say is that 96 out of 100. So I'm trying to decide how big to set this parameter, and I want to make sure that 96 times out of 100, I'm within 1% of the true optimum. That's the statement I'm making. So how would I decide how to set this MC count parameter, the number of Monte Carlo simulations, such that 96 out of 100 times I'm within 1% of optimum, given that my termination criterion is this. So I'm going to run, I'm not going to put an upper limit on iter count. I'm just going to do as many iterations as I need to. Okay, that's the part where I got stuck. I'm going to do as many iterations as I need to until this condition holds. And I want to make sure if I'm using this exiting criterion, 96 out of 100 times, I'm within 1% of truly optimal. So how big would you set the Monte Carlo count? What you can measure is the standard deviation of costs, approximately at least, and the average. So you can approximately measure these two things here. So here's what basically you can do. So how can we ensure 1% optimized gap with a 95.4% confidence? We want to choose K so that the variance of our average cost is within 2 sigma of the Gaussian distribution. So the my average cost when I terminate is going to look something like this. So all I'm saying is that I want to set the Monte Carlo sample number large enough that this width is about 1% of Z bar. If I do that, then every time I exit using the termination criterion I showed you, I'm within 1% of optimum. Okay, so I'm going to increase the number of Monte Carlo iterations, the capital K, such that this width here is within 1%, is 1% of Z bar. That's the idea. Okay, do you buy this? So basically what here, the problem is that this sigma depends on the K that I'm trying to set. What doesn't depend on the K, and intrinsically depends on the problem, is the average cost, and is the variance of the average cost. For example, in our problem over here, the average cost is 6.25, and the variance is 2 point something. It's you know, you have your model of uncertainty, you have an optimal policy which has a certain variance. That has to do with the problem and the problem alone. It doesn't depend on your Monte Carlo simulation. So that you can approximately compute. So that is data, that's K, independent of K. So we can approximate it at each iteration by doing these computations. And in fact, the sigma over there in the bell curve is related to the variance of the optimal cost through the following So basically, if I want to have this happen, then I just plug this formula into here and get the required K. Okay, are you buying the story? You're kind of buying it. Okay, so this is the K. Well, the bad news is here I'm getting a square of the inverse of the optimality gap, right? So that is going to, for a 1% gap, that's going to increase the number of Monte Carlo simulations by a factor of 1,000. So in my case of the problem I had earlier, if we compute here the Z bar is 6.17, the sample sample variance is 2.02, and the number required Monte Carlo simulations in each iteration is 4,300 approximately. I ran that yesterday. This takes about 40 minutes to solve for this problem. It's a lot of penalties that you're solving. Whereas what I showed you here is just 100 Monte Carlo outcomes, but then again, the confidence in my average cost estimate is not. Also, the amount of learning that happens with more Monte Carlo simulations is higher too. It's not, increasing the MC count doesn't only increase your confidence in your upper bound estimate, it also increases the number of trial X's that you use. So the number of cuts you generate for the value functions. So there's two benefits coming in. Now, I will try and get the project description and data. The project description, I kind of have it ready. The data, I need to lose a few more hours of sleep to set it up. And I should hopefully have everything ready by Friday. So in Friday, my plan is for us to see proof of convergence of nested decomposition. And I show you the project. We can discuss if you have any questions. And it's going to be SDDP on an energy problem. Okay?